First, I would like to thank the organizing committee for this kind invitation. And my topic today will deal with enamides and Ynamides as versatile building blocks in organic synthesis. Before getting into the heart of the subject, let me first introduce you the Ynamides and the tertiary Enamides. And I will start with Ynamides. So what is an Ynamide? An Ynamide is an alkyne directly substituted by an amine. This is in fact a very old functional group because it's almost 130 years old, but had only been characterized in 1958. This class of compound is very sensitive to hydrolysis and leads directly to the corresponding amide. So this class of compound is difficult to handle, difficult to store, and difficult to synthesize. Recently, Enamides have emerged as powerful building blocks in organic synthesis. So an enamide can be seen as an electron-deficient enamide. The electron-donating ability of the nitrogen atom polarizes the triple bond and allows radio and stereoselective reactions. The electron withdrawing group can act as a directing group, as a chiral auxiliary, or can even participate in the reaction. Enamides are bench-stable compounds. You can chromatography them and you can perform an aqueous workup. Enamides have been known for a long time since the pioneering work of Stork to create carbon-carbon bonds. But similar to enamides, they are highly sensitive to hydrolysis and are difficult to store. In contrast, tertiary enamides that bear an electron withdrawing group on the nitrogen atom are bench-stable compounds. They can be stored for a long time, but they are not inert. They have an enamidic activity towards epoxides, nitriles, or N-acylaminium ions. We have been interested in the reactivity of ketoenamides. Typically, we have a cyclic ketone, a carbon linked chain equipped with an enamide. We have shown that silver-catalyzed cycloisomerization of silylated ketoenamides led exclusively to bridged enamides. Without any silane enol ether, without any transition metal, in the presence of activated bromoalkynes, we obtained spiroenamides. These are relevant substructures of natural compounds. When the enamide is substituted with an ester function, we have both the E and Z configurated enamides. When the enamide is substituted with a phenyl group, this reaction does not take place. When the enamide is substituted with a phenyl group, you need triton B to perform this spirocyclization, and in this case, we have only E-configurated spiroenamides. So, considering the stereochemistry observed, this prompted us to study the reactivity of these compounds. Our first was to functionalize the carbon located alpha to the nitrogen atom by using allyl trimethylsilane and BF3 iterate. But instead of merely obtaining a new carbon quaternary center, we obtained more complex structures. First, this tetracyclic adduct having incorporated one allyl trimethylsilane unit with 52% yields and this pentacyclic adduct having incorporated 2 allyl trimethylsilane units with the creation of 4 stereogenic centers. So this reaction operates with a total stereo control by the creation of 1 or 4 new stereogenic centers. As you can see here, this tetracyclic adduct is a substructure of the alkaloid metathebainone, which belongs to the morphinane family. We then screened different Lewis acids to tune the selectivity of this transformation. And at the end, we found that with zirconium tetrachloride, we obtain preferentially this tetracyclic adduct along with a little amount of the pentacyclic derivative. Titanium tetrachloride with an excess of allyl trimethylsilane in a concentrated medium favors the pentacyclic adduct. Having found the optimized reaction conditions, we evaluated the scope of the reaction by varying the cycloalkanone ring. 5-membered ring and 6-membered ring were well tolerated. The 7-membered ring constitute the limit of the reaction because in this case, the reaction does not take place. And you can see here with the 6-membered ring, we are very close to the metathebainone structure. Concerning the pentacyclic adduct, again, 5-membered ring and 6-membered ring worked well, but this time the gem-dimethyl compound and the 7-membered ring were not efficient. We then focused on the substituents of the aryl group. Orthoderivatives and paraderivatives worked well. Surprisingly, unsymmetrically substituted aryl groups such as meta-derivative led only to 1 compound. In this case, the reaction is radioselective. With a naphthyl derivative and thienyl derivative, the reaction worked well, but with the later case, the yield is lower. Concerning the pentacyclic adduct, the yields are lower, but still acceptable for this domino reaction. With the thienyl derivative, we had only tetracyclic adduct, and with the naphthyl derivative, we had both a mixture of tetracyclic and pentacyclic adduct. Taking into account the stereochemistry observed, we propose following mechanism for this domino reaction. First, the Lewis acid activates the carbonyl function. Then, an intramolecular electrophilic aromatic substitution assisted by the tertiary enamide takes place. After rearomatization, ionization of the alkoxy Lewis acid complex, this tertiary carbocation is formed. Then 2 pathways are possible. With zirconium tetrachloride, allyl trimethylsilane adds on the glass hindered face on the convex face of the molecule. And then zirconium is big. The zirconium chlorine bond is labile, and so there is a beta-silyl elimination providing the tetracyclic adduct. With titanium tetrachloride, again, we have addition of allyl trimethylsilane on the convex face of the molecule, but this time the tertiary enamide traps the secondary carbocation to form this bridged compound, and then a second molecule of allyl trimethylsilane adds on the less hindered phase to the prochiral iminium ion. And after beta-silyl elimination, we observe the formation of the pentacyclic adduct. We have shown that imides equipped with enamides can be transformed into succinamidals equipped with tertiary enamides. By activation with a Lewis acid, the N-acyl-iminium ion is formed. Then this N-acyl-iminium ion is trapped intramolecularly by the tertiary enamide to form diazepines. N-head bridged head diazepines are relevant substructures because they exhibit interesting pharmacological profiles. For example, babicasarin and DC81 are psychoactive drugs. Arginine A and arginine B have antimicrobial activity, and antramycin is an antibiotic. Our idea was to transform the alpha-beta unsaturated ester into a divinyl ketone to install a cyclopentanone ring on our molecule through Nazarov reaction. The Nazarov reaction is a 4-pi electron process involving a cross-conjugated dienone to form a cyclopentanone by activation with a Lewis acid. Several research groups have been interested in this Nazarov reaction, especially concerning the substituent located beta to the divinyl ketone. For example, Denmark silicon-directed Nazarov cyclization was very successful for the total synthesis of natural compounds. Taking into account the beta-silicon effect, the positive charge is exclusively located at one termini of the allylic position, and after radioselective elimination, you got only one cyclopentanone. Our idea was to use the silicon-directed Nazarov cyclization to introduce the cyclopentanone ring in our molecule. So we transformed the alpha-beta unsaturated ester into the corresponding aldehyde. After addition of the Grignard reagent, we got the dienol, and after oxidation, we obtained the cross-conjugated dienol. By reaction with BF3 iterate, we indeed observed the formation of the tetracyclic adduct. Although efficient, this reaction sequence is very long, and the indicated yields could not be obtained in each case. So our idea was to synthesize an enamidal vinyl ketone to promote simultaneously the N-acyl-iminium ion trapping and the Nazarov cyclization. To synthesize the enamidal vinyl ketone, we used Garpur's procedure by using a catalytic amount of TAPCO. But in this case, we obtained a mixture of O and N alkylated compound. To avoid the O alkylated compound, we decided to transform the hydroxy group into an alkoxy group. And by the reaction with the triple bond, we obtained exclusively the desired enamidal vinyl ketone with 95% yield. But the domino reaction failed. The N-acyl-iminium ion trapping took place, but the Nazarov reaction was unsuccessful. Taking into account our previous results, we hypothesized that an enamidal vinyl ketone substituted with a TMS group would provide an efficient solution to solve the problem, by taking into account the beta-silicon effect to promote the Nazarov cyclization. So first we synthesize this enamide-on substituted with a TMS group. When the tosyl sulfonamide reacted with the triple bond in the presence of TAPCO, we obtained the enamidyl vinyl ketone. And when the cross-conjugated dienone was treated with BF3 iterate, we indeed obtained the tetracyclic adduct as only one diastereoisomer. We then screened different Lewis acid. We have shown that with the TMS OTF, we obtain similar results than with the BF3 iterate. In each case, we have the same yield. Having optimized the reaction conditions, we evaluated the scope of the reaction by synthesizing numerous imides. We obtained yields going from 41 to 89%. In each case, the reaction is totally stereoselective with the creation of 3 new stereogenic centers. With a 3-carbon linker chain, we obtain a polycyclic fused system incorporating 8-membered ring. With the methyl derivative, we obtained 4 new stereogenic centers. And with the 4-carbon linker chain, this compound constitutes the limit of the reaction because in this case, we only observed the eliminated compound. Concerning the reaction mechanism, the reaction sequence was uncertain. What comes first? Nazarov cyclization followed by N-acyl-iminium ion trapping, or first N-acyl-iminium ion trapping followed by Nazarov cyclization. Both would lead to the same compound. To get more insights into this reaction mechanism, Olivier Bistri and Laurence from ENS Paris performed cyclic voltammetry experiments to evaluate the affinity of the Lewis acid towards the enamidyl vinyl ketone or the aminal part. For this purpose, we synthesized 2 mimics, this alkoxy derivative and this enamidyl vinyl ketone. For the cross-conjugated dienone, the cyclic voltammetry pattern showed a reduction peak at minus 1.6 volt. When BF3 iterate was added, there was an evolution of the cyclic voltammetry pattern, and this time we obtained a reduction peak at minus 1.3 volt. When BF3 iterate was added to both compounds, there was no evolution of the cyclic voltammetry pattern, which means that the Lewis acid has more affinity towards the N-acyl-iminium ion precursor than towards the enamidyl vinyl ketone. So the cyclic voltammetry experiments are in favor of pathway B. First, N-acyl-iminium ion trapping and Nazarov cyclization. Finally, we could also isolate in one case the divinyl ketone, also corroborating the findings of the cyclic voltammetry experiment for pathway B. In conclusion, I showed you 2 domino reactions. From spiroenamides with zirconium tetrachloride, we obtained tetracyclic compounds, which are substructures of the alkaloid metathebainone, which belongs to the morphinant family. With titanium tetrachloride in a more concentrated medium, we obtained pentacyclic adducts by the creation of 4 new stereogenic centers. With enamidyl vinyl ketones, with BF3 iterate, we obtained cyclopentanone fused to diazepines stereoselectively. I would like to thank Dr. Clément Heinrich, who performed the first silver-catalyzed cycloisomerization, Dr. Frédéric Beltran, who performed all the spirocyclizations and the first domino reaction I showed you. I would like to thank Dr. Yongjong Zheng and Dr. Lucille Antna, who performed the second domino reaction I showed you from enamide vinyl ketones. I would like to thank Dr. Laurence Grimaud and Dr. Olivia Bistri, who performed the cyclic voltammetry experiments. I would like to thank Dr. Nathalie Gruber for the X-ray structures, and I would like to thank you for your kind attention.